So now we are going to see the current equation for JFET. So whatever current equation we have seen, it is an approximate current equation. So this equation we have been using it for JFET, right? ID equal to IDSS into 1 minus VGS by VP the whole square. So this is an approximate current equation. We are going to derive what is the exact current equation for JFET. Okay, and you have seen that the derivation is the exact derivation is a little bit complex, and so whatever approximation we could make, we have made and derived the drain current for JFET in the saturation region. But in BJT, the current the relationship is linear. You know, IC is equal to beta IB. IC is equal to alpha into IE. All the relationship is linear. But here you see in FET, the relationship is not linear. You have a power 2. I can say the FET is a square law device. Square law means the current is a function of square of voltage. So FET is a square law device. So it obeys square law. You can write in this equation can be written as I is proportional to V square in simple terms. I is proportional to V square. See here, ID is equal to IDSS constant into 1 minus VGS by VP the whole square. This is actually a voltage, right? So this I can write I is proportional to V square. So it is a square law device. And this equation, what you see here is an approximate relation for the drain current in JFET. And this equation is called as Shockley's equation. ID is equal to IDSS into 1 minus VGS by VP the whole square. When you put VGS equal to 0, that value of ID is called as saturation drain current, IDSS. Okay, and you know VP is the pinch off voltage. What is pinch off voltage? The voltage at which the area of the channel becomes minimum and a constant current will flow through the drain terminal. ID becomes constant at pinch off. When VGS becomes equal to VP, the drain current becomes 0. So I told you that condition is called as the cutoff condition. At cutoff, when the two PN junction depletion regions touch each other, there is no way for the majority carriers to flow through the channel. That condition is called as cutoff condition. Cutoff condition happens for VGS and pinch off condition happens for VDS. You have to be very clear on that. No confusion regarding that. So see in what you see, what the current equation you are seeing in the screen is going to be the approximate current equation which follows a square law dependence. Square law means you can see the current is proportional to voltage square. Usually in Ohm's law you have seen I is proportional to V. It is a linear relationship in Ohm's law, right? For a resistor, I is proportional to V. That constant you introduce, V is equal to I into R. Otherwise, voltage and current are in linear relationship. But in MOSFET or in JFET, the family of field effect transistors, what we see here is the current is going to be a square law. Current is going to have a square law relationship with the voltage. So ID is equal to IDSS into 1 minus VGS by VP the whole square. This is an approximate current equation. So in this equation, I told you when you put VGS equal to 0, that current is given by IDSS. So the approximate drain current is given by the last equation what we have seen. And now we are going to derive the exact drain current equation when we are going to start from Ohm's law. We are going to start from Ohm's law and we are going to consider N-channel JFET. See, this is the N-channel JFET I am considering from the of length 0 to capital L. So I am considering it is placed along x-axis from x is equal to 0 to x is equal to L. And this is the channel. This is the channel available for conduction between the two terminals. At the source, the channel height is minimum. At the drain, the channel height is maximum. And channel height is a function of distance. Okay, at the source, I call the channel height to be H1. At drain, I call channel height to be H2. And in between, I call it as H of X. Because the channel height continuously varies with X. And the maximum available channel height is going to be A. And you know this is an N-channel MOSFET, so you have an N-channel available between source and drain. And I'm going to apply VDS and VDS. So this diagram is interpreted in this way. Okay. We are going to consider this diagram for the entire current equation of deriving the entire current equation for JFET. Okay. So we are going to start from Ohm's law, and you know the resistance. The resistance is given by R is equal to rho L by A. And I say it is dr because channel length, dr because channel size is very, very small. So I cannot write R. It will be in the order of millimeters or micrometers, right? So I'm going to write dr. Dr is equal to rho into length. What is the length? The length is given by dx. See, I'm going to take a small portion of my length. That's why I'm writing dx. So finally, I'll integrate from 0 to L for getting the entire length of my device. Okay, dr is equal to rho, resistance formula is rho L by A. So dr is equal to rho dx by A of x. And here you see everything is a function of x because the channel height is not uniform. The channel height is constant. I won't write it as A of x. I will write it as just as A. Correct. But since the channel height is not uniform, it depends on the length of the channel. I'm going to write everything as a function of x. Rho is the resistivity. A is the cross-section area. By neglecting the minority carriers, FET is a unipolar device. I will not consider the minority carriers. I'll consider only the majority carriers. Channel resistivity is given by rho is equal to 1 by q mu n nd. And rho is equal to 1 by sigma. And sigma value, it is q into mu into nd. It is the normal formula relating your conductivity and your doping concentration. Resistivity is 1 by conductivity. See, this formula sigma, we have been studying it from unit 1, right? The same thing will follow till the semiconductor, whatever we are going to learn. And the cross-sectional area A of x is equal to A minus H of x into W. A is going to be the complete area of your N channel. And this area is not constant. It depends on x, right? So total area of channel is going to be the total height. From that, I'm subtracting this H of x. So I'll get the remaining height in this region. So this region, I'm going to find the area. So the total height is A minus H of x if I subtract, and if I multiply by the total width, I get the total area. So A of x equal to A minus H of x into W. Area, it is length into breadth. So A is the channel thickness or height of the channel, and W is the width. Width is along the x-axis. So A of x equal to A minus H of x into W. I am considering the area of this inner side. So the total area, total height is A. And from A, if I subtract H of x, I'll get this area in between. So that is why I've written A of x equal to A minus H of x into W. Area equal to length into breadth. And now substitute everything. So dx equal to dr equal to substitute for rho and A of x. Rho is here and A of x, what we have got the equation here. So dx by q mu n nd into A minus H of x into W. So I can write the differential voltage across the region as per Ohm's law. V is equal to I into R. The differential voltage, I write dV of x equal to d I1 into dr. ID1 into dr. ID1 is the drain current which is flowing through the channel. So I'm writing this from Ohm's law. Okay, in Ohm's law, V is equal to IR. So I'm writing the differential voltage dV of x equal to ID1 into dr. Now substitute this IDR in the place of, substitute this dr here in the place and find out dV of x. So dV of x equal to ID1 into dx by q mu n nd W into A minus H of x. So I can find I cross multiply ID1 into x dx equal to q mu n nd W into A minus H of x into dV of x. Okay, cross multiplying, I get this equation. See, step by step, everything is simple substitution. It's very, very simple.